So we've started a discussion on linearized general relativity. The idea is that we want to look at situations where the metric is just slightly deviated from the Minkowski metric. This will cover our applications to gravitational waves far from the source. And we have a bit of work to do, and we're going to do it by the way of Einstein field equations, just to get used to the Einstein field equations and understand their content. Okay. Later we'll be looking at strong gravity, the opposite situation here. Okay, in those situations where the curvature is high, okay, and the deviations from Minkowski metric is very large. Here, our metric is the Minkowski metric plus a small deviation h mu nu, which is much less than 1. And so we discussed this last time, and now it's time to get into the guts of it. So let's do that. Okay. So we're interested in deviations from the Minkowski metric, and there are two varieties of that. There are varieties where we have Lorentz transformations, which make a deviation from the Minkowski metric, and we also have the situations where we have infinitesimal general coordinate transformations. Okay, and so we know in full general relativity, we'll have general coordinate transformations of a rather arbitrary type, and here we're just interested in small ones because we're interested in gravitational fields which deviate from the Minkowski metric by a small amount. Okay, in Minkowski metrics itself, such as special relativity, we understand Lorentz transformations, and let's take a look at how Lorentz transformations affect a metric which is just slightly deviated from the Minkowski one. So in each case, 1 and 2, we apply a Lorentz transformation on an infinitesimal general coordinate transformation, and g goes to g prime plus h prime. Okay, the new metric and the new deviation from the Minkowski metric. In case 1, Lorentz transformations, well, we've studied that intensely when we did special relativity, and we know the Lorentz transformation, the boost, and I'm just writing it in abstract form here with coefficients which are lambda, mu nu, and I know how to write down lambda mu nu in terms of the velocity of the transformation between two inertial reference frames. So check on your supplementary lecture number 11, which writes down lambda in more detail. All I need to know here is that lambda are just constants, and then I can do my formalism here. Okay, so this is my transformation from one frame to the other, and in that transformation, my metric changes from g to g prime. Okay, it does so as a second rank covariant tensor, and I know how that transformation works. We looked at how covariant vectors transform, and then we inferred how covariant tensors of multi-indices are transformed as well. Okay, and so I've written it down here, and again I remind you that in the video lectures I'm writing down the formulas with the Einstein summation convention. In the supplementary lecture number 11, I'm writing out the summations. So here, for example, a repeated index is summed over. I have a repeated index of rho summed over. I have a repeated index nu that's summed over, and okay, and there you go. And mu and nu are held constant throughout the calculation, and this is just the way the second ranked tensor g mu nu, which is covariant, transforms. Okay, so in this particular case, x prime is related to x by a Lorentz transformation of constant coefficients lambda, and so I can calculate these derivatives. That just isolates the particular lambda values. Okay, and so I put that into the formula here. G is just eta plus a small deviation called h, and I put that in. Okay. Okay, so I have two terms where lambda applies to eta. Okay, well that's just the the problem in special relativity where I boost from one frame to another, and I recall that under such a boost, the metric of space is left invariant. Okay, I go from one inertial frame to another inertial frame. Okay, the metric in both of those frames is the same. Okay, the physics is the same in both of them. Okay, and so the this product applying to eta gives me eta back. Now remember when we discussed special relativity, we simply showed that explicitly. Eta is a very simple matrix, minus one on the diagonal, okay, with a plus one in the 0, 0 component, and that with a lambda applied to it just reproduces itself. Okay. Well, that was built into the formalism. That's just an expression of the fact that the speed of light is the same in both frames. Okay, and so I go on the right hand side, I get eta, and then I get a new h, okay, which is a lambda applied to h, and I've written it out over here. So it's just a transformation on h, and I call the result h prime. Well, it's an admissible coordinate system as long as h prime is much less than 1, and so I'll keep that in mind. Okay, so that's a Lorentz transformation which preserves the fact that that my Minkowski metric deviates from the real metric by a small amount, and that'll be true as long as h prime is much less than 1. Okay, this inequality, okay, that h be much less than 1 is of course frame dependent, coordinate dependent. It's not going to be true in every coordinate frame, certainly, and so I want to look at this. I want to look at the space of coordinates, which leaves that invariant. Okay, I want to look at the coordinate systems where it's true, where I can apply the ideas of small deviations from Minkowski space, where I can apply the ideas of linearized general relativity. Okay. Well, in case 2, I have infinitesimal general coordinate transformations. Okay, so I might be making local rotations in my coordinate system here. They're spatially dependent. Okay, and they're going to change my coordinate system. Okay, and I've written that down here, that x prime is equal to x plus a small amount, and the small amount is on the scale of h mu nu, which is much less than 1. Okay, so I make small coordinate transformations, okay, which will preserve the fact that my metric is just slightly deviated from my Minkowski metric. Okay. Okay. Well, so if x prime is equal to x plus eta, then I can differentiate this expression and tell you how these derivatives depend upon chi. Chi is the deviation of x from x prime. It has to be small, as stated here. Okay, so I can plug these derivatives into my transformation law for the metric and get the new metric in terms of the old metric. So I see that g prime is equal to the old metric, which is eta plus h, and a change. And the change you see is this collection of derivatives of chi. Okay, okay. So that's simple. Okay, so I end up with g prime is equal to eta plus deviations from eta. The deviation from eta, then I call h prime, and h prime in the new coordinate system is h. Okay, and then corrected by the infinitesimal coordinate transformation I'm calling chi. Okay, so there you go. I know how to make these transformations. These transformations are symmetries of the theory, and I need to know that so I can study the Einstein equations of motion. A technicality here is I note that g is equal to eta plus h, which h is small, and so, for example, g with the upper indices, that has to be the inverse of g with the lower indices, And I see that that's eta with the upper indices minus h with the upper indices, where g is eta plus h with the lower indices. And okay, and that's a sensible conjecture, and I verify that conjecture simply by taking the contraction of g with the lower indices and g with the upper indices and getting the Kronecker symbol. I'm doing linearized general relativity, and so I want these equalities to be true through first order. Okay, that's all, just through first order. And then plugging these in, it's easy to check that in fact g upper, g lower contracted is delta. Okay, if in one case I have plus h and the other case I have minus h. So the linear terms cancel out. I'm left over with second order effects. Second order effects are thrown away, okay, because I'm doing all of my arithmetic to first order in h, and that's all I need. So this is very handy, you see, because now I know how to write g with lower indices and g with upper indices, and I can then apply that to my reduction of the Einstein field equations. I have a lot of arithmetic to do now, you know, and we're studying that arithmetic just to get us used to the Einstein field equations. At the end of the day, we'll point out that there are easier ways to do this sort of thing, but I don't care about that. What I care about is learning about the Einstein field equations in weak field situations, understanding the Einstein field equations in strong field situations, and just getting a mastery of that subject. Okay. In the case of weak field situations, special relativity gives me another viewpoint on it, but I'm not pursuing that now. Okay. We'll say a few comments about that though. Okay, so now with those preliminaries done, I can come back to my field equation, just the Einstein field equation, written in terms of the Ricci tensor, like this, and start working on it. I want to work on the left-hand side, and I want to see how the left-hand side behaves in the situation that my space-time is the Minkowski metric with small deviations. That's going to be very useful in approximations because lots of situations of that character. For example, the gravitational radiation far from the source. That gravitational radiation is a very small perturbation on Minkowski space-time, as we'll see. So I need to know this. In addition, I might be doing planetary orbits, and I want to know the evolution of the planet of Mercury, for example, as a function of time. Well, the deviations from Newtonian physics are very small, implied by general relativity, and so again I need the linearized field equations to get those answers. I don't need to face the full Einstein field equations to do that, because the deviations from Newtonian physics are very small. Okay, so that's what I'm headed for. Okay, so in order to calculate the Ricci tensors and the Ricci scalar, in the case where my space is Minkowski plus small deviations, I want to write out R in terms of the Christoffel symbols and simplify them appropriately. So we write on the right-hand side to first order in H. Okay, I start with my Christoffel symbols and I write them down here. Right. So remember, we have the Christoffel symbols written in terms of G, a general metric, which could be very far from the Minkowski metric. And now I replace G by eta, the Minkowski metric, plus small deviations. Okay. And so when I do that, I get this expression over here. Okay. In this parentheses, I have just gradients of G mu nu. The gradient of the Minkowski metric is 0, of course, it's just constant. And so I get something which is explicitly first order. Okay, in the general formula, then this eta would be G, the exact metric. Okay, but you see, I can replace the exact metric by the Minkowski metric because I'm only interested in calculating the Christoffel symbol first order in H. If I kept here instead of eta G, which is eta plus H, then I'll then I'll be accumulating for the Christoffel symbol terms which are of order h, terms which are order h squared. But I'm not tracking terms of higher order, of order h squared, so I can replace g in the g, which raises indices by eta. I made that point before, and now we see it very, very explicitly. So I write this as Christoffel symbol is equal to this stuff plus of order h squared. I didn't leave that. I didn't write that in here because that's implicit in my approach. Okay, so here's gamma. I write it down. Now I need to get to the Einstein field equations. I need the Minkowski. I need the Riemann curvature tensor for all four indices, and I have the formula for that in terms of the gradients of the Christoffel symbols plus products of the Christoffel symbols. Okay, so I write it down like this. Well, the terms which are second order in the Christoffel symbols, I don't need to write down because you see the Christoffel symbols here are already first order in h. So this stuff here is second order in h. Throw it out. It's of order 0. I'm not tracking it. I'm getting my physics to order h. Okay, so this is what R is. And then I have a lot of algebra to do, and this is done in your supplementary lecture number 11, okay, where you put in for gamma here, you take these derivatives, and you have a lot of algebra to do. Okay, it's straightforward, it isn't so bad, a couple of lines, not so bad. Okay, so I do that, and then I'll get the left-hand side equal to proportionality T mu nu, and that's what I've written down here, you see. I've written it down here with a factor of 2 coming from the left-hand side to the right-hand side. And on the right-hand side, I see various derivatives of h. Okay, because it's coming from this term. Okay, it's not so bad. Here, when I see h, remember, h without any indices is the trace of h mu nu, and I've written it down like that. Okay, that comes out from all of these indices contracted appropriately. So here's my wave equation, or my Einstein field equation. It's a god-awful mess, isn't it? Well, now I want to, so I've tried to make some definitions to clean it up a bit. Okay, and if you look at that a long period of time, you'll see that if I define h bar by h minus a half eta times the trace of h, it cleans it up a little bit. Okay? So I substitute h bar. I get rid of h mu nu in terms of h bar by just substituting away and cleaning up. Okay, and then in the supplementary lecture 11, I show more of the steps of the algebra, okay, and I show that even in terms of h bar in general, the equation is rather disgusting. It's still kind of tough. But what I see, something I notice right over here, that a lot of the extra terms are the form divergence of h, okay, divergence of h. So if somehow I can choose the divergence of h bar to be equal to 0, I'm going to get a simple equation. So I go to h bar to get rid of these terms that depend upon the trace of h, and then I impose the gauge condition that h bar is divergence free. Then in fact I find a wonderful wave equation. Okay, just the wave operator, the del Ambertian, hitting h bar is equal to T mu nu with the constants there. But why did I think of all of that? Okay, well, I thought of all of that because it looks just like electrodynamics. In electrodynamics, I remember that I have a wave equation for the 4-vector a mu nu. Okay. Okay, and so it's in general not very simple. Okay, it's an equation which tells me a mu nu on one side is equal to, okay, j mu nu on the other side, the source of the electromagnetic waves. Okay, however, it cleans up tremendously if I choose the Lorentz gauge, the gauge where the divergence of a mu is equal to 0. Okay, so I notice a similarity between weak field gravity and ordinary electrodynamics. If I choose the Lorentz gauge, in electrodynamics, I get a very simple wave equation. Okay, that del inversion on a mu, that's the wave operator, on a mu is equal to j mu. Okay, and remember from a mu I get physics by way of taking the four divergence and then making the electromagnetic tensor. Okay, so I try the same thing in gravity, and lo and behold, it works out in detail. And I leave some of those details to the supplementary lecture, where I do all of that and show that it all works out very nicely. Okay, so here it's discussed. Can we really make these choices? Okay, can we really impose that the four divergence of h bar is equal to 0? Okay, the field equations, I'm writing them now down in general terms, in terms of h bar. I wrote down the equation in terms of h, and I defined h bar. Okay, it's a very simple relationship. Okay, and then I put it in, and I saw that wave operator on h bar is one of the terms, and then the other terms are all proportional to stuff, which is of the form divergence of h bar, divergence of h bar, divergence of h bar. And then on the right hand side, I have my source. Okay, and I remind you here that h bar is related to h by this definition. Okay. One of the things that's useful to notice is that I can invert this relationship. I can get h bar in terms of h, and also I can get h in terms of h bar. Okay, so let's do that because it's going to be useful in our later exercises. Okay. So can I invert this expression? Well, for example, take the trace of it. So raise one of the operators and sum over it. And that's what I've done here. And then you see that h bar, the trace of h bar mu nu, is equal to minus the trace of h. Okay, just do this. So h bar mu nu is a trace of h minus a half trace of eta h. Trace of eta is 4. Okay, right? Eta with upper and lower indices is just delta, and so the trace of it is 4. I put that in here. Okay, so h bar is h minus 2h is minus h. Okay, so I clean it up. I learned that the trace of h bar is minus h. I put that into this formula. H is minus h bar. Okay, and then I can invert it. Okay, I see that this thing can be written in terms of h is equal to h bar minus a half eta h bar. So both formulas look the same. Okay, because h is equal to minus h bar. Okay, well, I'm juggling definitions here and I'm fiddling with the indices. So take a look at that in the supplementary lecture number 11, and you'll sort of get used to it and see the rationale between these various definitions. I'm just trying to look for a conventional, useful language so I get a simplest possible equation of motion for Einstein field equations in this kind of situation. Okay. So here's the Einstein field equation written in terms of h bar. It would really be nice if I could choose that the divergence of h bar is equal to 0. Okay. When I say that, I mean with all of those indices. When I say divergence of h bar, I mean sum over eta gradient d rho applied to h bar mu rho is equal to 0. Remember, h bar is symmetric in mu and rho, so it's going to it'll be true for this situation, and it'll be a situation where I write down h bar of the indices in the opposite order. Right? Now my metrics are symmetric. Okay, in all of these cases, my Minkowski metric is symmetric. My deviations from the Minkowski metric are symmetric, and so I don't have to watch all of those details. Okay, now the question is though, okay, can I always choose h bar to be divergence free? Okay, so let's imagine a coordinate transformation that takes h to h bar, and let's try to make h bar have no divergence. I might start out in a coordinate system where h has a divergence. I don't like it. So I'm going to just make a coordinate transformation and try to get to a frame where H prime has no divergence. Here's how I transform from one frame to another. Okay, from H to H prime. Okay, that's fine. Now, what's the transformation for H bar? Well, I know how to construct H bar. H bar is H minus a half eta H. So I just do my arithmetic here. Okay, if I know how H transforms, I know how the right hand side transforms. I know how the trace transforms. Okay, the trace just being H upper mu lower mu summed over. And so I can then see that H bar transforms in this way. It has the same structure, okay, plus an additional structure coming from the trace. Let's turn off it here. Okay, and that's simple arithmetic. Nothing special about it. And check it in detail by following along in Supplementary Lecture 11. Supplementary Lecture 11 follows this development, okay, in detail, and it gives you the extra details that I don't want to put up on the sheet because it's just too much indexology. Okay, so here's the change of coordinate system for H bar. Okay, and so then I can see what the coordinate transformation is for the divergence of H bar. I just take the divergence of both sides of this expression, and I see the divergence of H bar is equal to the divergence of H minus wave operator on eta. Okay, these three terms just coalesce into that term using just the arithmetic that goes into it. Well, that's sort of nice, because now I can see that I can set the divergence of H prime equal to 0 as long as I choose that the wave operator applying to my transformation, my coordinate transformation, is equal to the divergence of H in the original system. And that's what it says here. Okay, so the point is I can always choose H to be divergence free. Now this is just like electrodynamics. I always go to the Lorentz gauge. Okay, I always know it's possible. So I never discuss those other gauges, right? I always write down the equations explicitly in terms of the Lorentz gauge so that all the ugly terms are gone. And I take the same approach here. Okay, so I drop the primes and I just say I'll work in the Lorentz gauge. Okay, and in that gauge, wave operator on H bar is equal to constants times T mu nu. And also, in that particular gauge, I also learned if I take the divergence of both sides, since H bar satisfies the gauge condition, the Lorentz gauge condition, T mu nu does also. And so the divergence of T mu nu is equal to 0. Okay, so that's the basic equation of linearized general relativity. Okay, so you give me a source and I'll get you an H bar. And the H bar will be a useful approximation to the full problem as long as the non-linearities are small. Okay, that covers a great many special situations, and so that's very useful. Okay. Now, as I've said before, this is only to first order, and to first order, then you don't have the full consistency of the Einstein field equation, and that's the comment at the bottom. See, this is the ordinary derivative applied to t is equal to 0. Remember, in the full discussion of the Einstein field equations, we would have had the covariant derivative of t equal to 0, and then we would have implied that the mass points travel on geodesics established by the gravitational field, which is implied by the source. Okay, here we've lost that information. This is just an ordinary conservation law. You see we don't have the gravitational field implied here, and so some of the self-consistency of full relativity is lost, so we better be careful about it. But look, this is not a big deal, because we do this all the time in electrodynamics. In electrodynamics, radiation problems, we imagine a source, a radiator juggling charges around in some external fashion. I specify that motion by some external sources, okay, and then it radiates away, okay, and then I calculate the radiation away by use of my linearized wave equation, okay. I don't insist upon complete self-consistency, and I do the same thing here, okay. Well, maybe it's a bit of a greater sin here because general relativity is an intrinsically a nonlinear theory, but still, that's what I'm going to do. I'm going to be interested in using this linearized equation in the case of the generation of gravitational waves. I'll take a model for the source of the gravitational waves, just a binary of neutron stars spinning around one another, losing their energy to radiation in gravitational waves, so they lose their energy and they spiral into one another, and then all of a sudden they hit one another and they merge in a great big mess, okay, which generates more radiation, okay. But I'm always looking very far away from there, and so if I treat that source as an external source, okay, I can still get my wave very far away. Okay, now a purist will do better than that. He'll solve the full Einstein field equations in the vicinity of the binary system, which is losing energy, losing spatial distance between the members of the binary because energy is going away, okay, and then finally they merge, okay, and then they calculate the radiation coming out from them, okay. So they have to deal with the strong forces and the strong deviation from Minkowski space in the vicinity of the binary. Well, we're not going to look at that. We're just going to make a model of that, and then we're going to look at the gravitational wave very far away. Okay, so we'll capture a lot of the physics, most of the physics, by our procedure. But if you want to do a full quantitative job, which gives you also the amplitude of the radiation very far away, you have to do a better job. So there's something for you to look forward to. That's not a bad idea. But we'll do what we can do, and so be it. Okay. Well, one of the things I want to do is just do a simple application, make sure that I haven't made a terrible mistake. Okay, before I go back to gravity waves. Okay, and I just want to check an easy application. So I'll choose a static problem with non-relativistic motion, and let's just check that the linearized gravity gives me what I expect, which is the ordinary Newtonian description of gravity. Okay, so I'll take a static problem with non-relativistic motion. We should retreat Newtonian physics. Okay, so in my previous equation, the only large component for the energy momentum tensor will be the T00 component, which goes to rho c squared. And so my full wave equation reduces down to just the Poisson equation if we identify h bar 0, 0 is 4 Newtonian potential divided by c squared. Okay, so it all works out perfectly fine. So I'm looking at a static situation, so the D'Alembert operator just becomes minus del squared, okay, just minus the Laplacian squared, and it reduces down to this if I take h bar 0 equal to 4 Newtonian potential over c squared. So now, so that teaches me how to identify h bar 0, 0 with Newtonian physics. Okay, that's fine and dandy, but h bar is not really what I'm interested in most cases. What I'm interested in most cases is h, because that's the deviation of my metric from the Minkowski metric. Okay, so I want h mu nu. Okay, but I remember that h bar is related to h by my basic equation that h bar is equal to h minus a half eta h, where h is the trace. So if I want to get h, just go back to those equations and figure it out. So for example, the trace of h bar is equal to this term, Okay, the only big term is h0, 0, and so in the trace, I only have to follow the mu equals 0 component, and that's 4 times the Newtonian potential over c squared. Okay, but we had that h bar is equal to minus h, and so now I know the trace of h. It's just minus 4 psi over h bar. Okay, so I'm making some progress. I want to get h. I want the other components of h, the deviation from the Minkowski metric. Okay, so I go back to my definition for h bar, and I write it down for 0, 0, like here, and I infer that h0, 0 is twice psi over c squared. Okay, okay, because I know all of the bits here. I know h bar 0, 0, right, is 4 times psi over h bar. I know the trace that's given by this, so I know h0, 0. Okay, that's great. So I know the 0, 0 components are the deviation of the metric for the Minkowski metric. Now I want to know the deviations for the xx term and the yy term and the zz time. So that's what I write down here. Okay, so I just write down my relationship between h bar and h for the 1, 1 components. Well, that's easy to write down. Okay, I know eta 1, 1. I know that that's minus 1. I know what h is. I know it's minus 4 psi over h bar. Okay, so I can calculate then h11. Okay, okay. So on the left hand side I have h bar upper 1, 1. But remember, from this equation here, the only large term is 0, 0. So the h11 term is essentially 0. It's lower order. Okay, so that tells me that h upper 1, 1 is equal to twice Newtonian potential over c squared. Okay, and then similarly I get 2, 2 and 3, 3 in terms of Newtonian potential. Okay, so that's great. So now I can go back and write my metric in terms of g mu nu times dx dx. And I do that and write it down with h11 equals h22 equals h23 is this. And where h00, where is that sucker? Somewhere around here. h00 is twice this as well. Okay, and I see that the weak field static metric, okay, for general relativity has this form right here. Okay. So it's ds squared. I have a term that goes like dt squared, and the coefficient is 1 plus twice twice the Newtonian potential over c squared, and then in front of the Cartesian terms for the spatial metric, I have 1 minus twice Newtonian potential over c squared. Okay, so check the supplemental lecture number 11 for the details. Be careful with your signs, and you'll get that, and that's very useful, because now we have the metric that's going to apply to lots and lots of problems. Okay, this is now the metric for any situation where the gravitational field is small. Okay, in this particular sense where h is much less than 1. Well, that covers the solar system, for example, and with this metric, then I can calculate, for example, the precession of Mercury. With this metric, I can calculate the deviation of light around a star. Okay, and those things are done in your textbook. Okay, okay, and this metric is correct to order 1 over c to the 4th. It's called an isotropic metric. Okay, and it's very useful. Now you might write this in a little more interesting fashion. You might see that ds squared is equal to look at the 1 terms. It's just the Minkowski metric, and then the Minkowski metric is corrected by 2 phi over c squared times the Euclidean metric for 4 space. Right? Euclidean. Why? Because there's a plus, and over here I have minus minus, that's a plus. So the deviation from the Minkowski metric is twice phi